All right, let's take a look at problem 3 or example 3 from chapter 5. So use the SRK equation to calculate the following properties of isobutane. And so we'll just take it one at a time. Okay, and so in A, we're asked to calculate the residual enthalpy and entropy at a pressure of 10 bar and a temperature of 300 Kelvin. All right, now, we're dealing with isobutane again, which is exactly what we just looked at in problem 2. And so I have my problem 2 solution up, right, just because as a reference, is we had that at 300 Kelvin, the saturation pressure was 3.7 bar. Okay, so in A here, we're at 300 Kelvin and 10 bar, so our pressure is greater than Psat, so we're going to be a liquid. Okay, and, same comment as compared to in problem 2 is in this course, right, I've been giving you reference points to be able to identify the phase. So if you get more than one real root, you can identify which root or make be able to select which root to use. Next semester, we'll get into phase equilibrium and stability. And the key will be is now that we have our SRK equation of state updated to calculate HR and SR, is I could also calculate GR. GR is equal to HR minus TSR. And then when you get more than one real root, you can just compare the values of GR. Right? The phase with the lower value of GR, or residual Gibbs free energy, is your phase that you have. Okay, now GR is equal to RT log V, so the smaller the GR also corresponds to the smaller the fugacity or fugacity coefficient. Okay, but that'll be next semester, right? So we had confirmed that we have vapor-liquid coexistence by the residual Gibbs free energy. Those two phases would be the same. Otherwise, if I have more than one real root, it'd be the phase with the lower Gibbs free energy, residual Gibbs free energy, or molar Gibbs free energy would be the phase that I have. Okay. But anyway, so for A here, I have a liquid. Okay, now key is, in terms of calculating residual properties with my equation of state, is I have this black box. Okay, and in goes, I need my temperature and pressure, and then I need parameters Tc, Pc, and omega. And then out in the context of chapter 2 is going to come my molar volume, compressibility, then it also returns the ideal gas molar volume. And now this is updated in chapter 5 to also return HR and SR. Okay. All right, so to perform this calculation, I'm going to jump over to MATLAB. And what I have downloaded my directory is this is my function. And so this is my function file, which actually does the SRK equation of state calculation. Okay, I'm going to close it because I don't want to touch it or edit it, but you need to download it and have it in your working directory. Then I also downloaded the script example 510, right? And what this is when I wrote my SRK equation of state code, I wrote it and applied it to example 510 in the book. Right, example 510, so that the book provided a solution, so I could use that to confirm that my code was correct. Okay. And so I'm going to take that script that I have for 510, and I'm just going to create a copy. So I'm going to do a file save as, and I'm going to call this chapter 5, and this is example 3, so I'm just going to call it chapter 5.3, and I'm just going to update this for this problem. Okay. All right. So for my black box, I need Tc, Pc, and omega. So to get those, I'm going to head over to Appendix A. So this is Appendix A. And it's at isobutane because we had isobutane for the last problem, problem 2. And so I need Tc, 407.85. So Tc's 407. 407.85. Come on. 407.85. Pc's 36.40. And the eccentric factor, omega, is 0.186. Okay. Then in my temperature, okay, that was 300 Kelvin. My pressure was 10 bar. Okay. Cool. Okay. And then this, right, here's my function, with these parameters that need to be passed to it. And then here's the variables that are going to get returned. I'm just going to put a tilde in for VSRK since I don't need the molar volume. I also need the ideal gas volume, so I'll put a tilde there, but I'll keep S. That way, if I get more than one real root, I can look at it and use that in my selection. Okay, so now I run it. Bam, I get 3 real roots. Okay, so I need to choose which root I have. Okay, and we're going to choose the third root, which corresponds to my liquid. Okay, and so let me suppress this. Okay, so I'm going to select liquid root, and at the same time I'm going to convert HR to kilojoules per mole since the value is rather large. Okay, so HR is going to be equal to HR SRK, and then I'm going to select the third root. Okay, and I'm going to divide by 1,000 to get that in kilojoules per mole. And then SR is going to be SR SRK. And I'm going to choose the third root, which corresponds to my liquid. Okay, HR. Okay, so again, I'm being a little fast because this is just the same as in the last problem, but HR is units of joules per mole. Okay, so I've divided by 1,000 to get to kilojoules per mole. SR has units of joules per mole Kelvin, so I'm just going to keep that as is. Divide H by 1,000 just so the value becomes a little smaller. Okay. So I get HR and SR. Okay, so cool. So let's go ahead and record those values up here. Okay, so I get HR is equal to negative 20.0175 kilojoules per mole. Okay, that's HR. And SR is negative 57.9517. Okay, and that's joules per mole Kelvin. Okay. All right, so that's part A. Okay. All right, now part B. So part B asks us to calculate the enthalpy and entropy at 10 bar and 300 Kelvin, so at that same temperature and pressure, using as a reference date the saturated liquid at 1 bar. And so saturated liquid at 1 bar, right? So, so saturation temperature is 266 Kelvin. So that tells me is at 1 bar and 266 Kelvin, I have vapor-liquid coexistence. And so I would calculate, I'd get 2 enthalpies, say at 266 Kelvin in 1 bar. One would correspond to a liquid, one would correspond to a vapor. So I want to compute my enthalpy relative to the enthalpy of the saturated liquid at that temperature and pressure. All right, so we're going to go through our reference dates in glory detail just because sometimes it could be confusing. Now the key is thermodynamics is a subject of differences, right? So I think about my first law of thermodynamics, delta U is equal to Q plus W, right? So thermo is all about computing differences. Okay? Where these absolute quantities come in is it's just a matter of convenience, right? Sometimes it's convenient to define something in, say, absolute terms that makes it easier in terms of tabulating data. Okay. So, but thermo is just a matter of differences, right? So there's no such thing as an absolute enthalpy. It's enthalpy relative to something, right? And so it's just a matter of how I define that something that I'm computing it relative to. Okay. So let's try and do this, right? So how I start is I'm going to write this as H, right? My enthalpy of interest minus H naught, right? Calculate differences in enthalpy. Then in the context of chapter 5, I take my differences in enthalpy and I write it as ideal gas contribution, so difference in ideal gas values, plus a residual contribution, HR minus H naught R. Okay, so I take my difference and I write it as an ideal gas contribution plus a residual contribution. Okay, and then on the next line, I'm just going to bring H naught over. Right, so H, right, this absolute quantity that I'm trying to compute, is equal to H ideal gas minus H naught ideal gas plus HR minus H naught R plus H naught. All right, so now what do I do? Well, in this problem, right, so not, right, this not, right, so state 0 is going to correspond to, right, a state at, 1 bar and 266 Kelvin. Okay. But what I'm going to do is we're told to, use as a reference state the saturated liquid at 1 bar and 266 Kelvin, right? So that's going to correspond to the actual state, right? So H naught, which is the enthalpy of my actual state at 1 bar and 266 Kelvin, I'm going to take it to be 0, right? So I'm defining the actual properties at state naught to be 0. Okay. So then in that context, right, H, okay, this absolute H, which is really H relative to H naught, I'm just taking H naught to be 0, is equal to H ideal gas minus H naught ideal gas plus HR minus H naught R. Okay. And, again, when I look at this, okay, when I have differences in residual, okay, my residual values, those could be calculated using my SRK equation of state, just as we did in A. I'll just need to do another calculation to get H naught. Okay, H naught just at T naught and P naught. All right, so T naught's 266 Kelvin. P naught's equal to 1 bar. Okay, and we're going to assume, right, this is going to be a liquid if we have more than one root, which we expect. Okay, then when I have difference in ideal gas values, right, I'm thinking of analytic expression, right? So difference in ideal gas contributions can be computed using an analytic equation. Okay, well, what does that look like for H? Well, for H, okay, the key is H ideal gas minus H naught ideal gas. Okay, that's going to be integral from T naught to T of Cp ideal gas dt. Where in our problem Cp is constant, so I could pull it out. And I'm just left with Cp ideal gas T minus T naught. Okay, cool. So we're given the value of Cp ideal gas. Okay, that's in the additional information. It's the same value from problem 2. We're told Cp is constant, which is why I pulled it out. And then we're given the value, 96.5 joules per mole Kelvin. Okay, so my ideal gas difference is just Cp dt. And then we've already computed HR, but I can get H naught R using our cubic equation of state. Okay, so that's that. Okay, let's get our equation for S before we jump over to MATLAB and solve. So to get S, okay, well, it's S is going to be, we're going to end up with the same equation. So it's going to be S ideal gas minus S naught ideal gas plus SR minus S naught R. Okay, and so same thing. Okay, we'll compute this using our code for our SRK equation of state. Okay, and then when I see this difference here, I'm thinking analytic equation. Okay. All right, but now it's a matter of, well, how am I going to go about computing this? Well, in this case, this could be a little more involved, but we got this. Okay. All right. So how we're going to compute this is, well, I know my first law, right, is delta U is equal to Q plus W. Okay. And now if I write this in my differential form, I'm going to write du is equal to del Q plus del W. Okay. Or if I assume my only work is boundary work, okay, then del W is going to be equal to negative P dV. Okay, cool. All right, so now solving for del Q. Okay, del Q then is going to be equal to du plus P dV. Okay. All right, so I have del Q is equal to du plus P dV. Now, if I assume that the only heat exchange between my system and surroundings is reversible, well, then for that case, del Q is equal to T ds. Okay. So solving for ds then, right, so in general, ds is equal to 1 over T du plus P over T dV. Okay. All right. So as we go through this process, right, it's could be a little longer and a little more cumbersome in the context of this course, but we do it once and we have it. And then next semester, when we do a lot more work with property relationships and definitions, it'll become a little more straightforward. But all is the same and good. All right, so now for the case of an ideal gas, okay, so what I want is the ideal gas contribution. ds ideal gas is going to be equal to 1 over t, and actually, before I even write it as 1 over t, right, for an ideal gas, du is just CV ideal gas dt. So this would just be CV ideal gas over t dt, okay, plus p over t dv. Now, I'm going to simplify this term before I integrate it, because if I were to integrate this from my, V naught to my volume of interest, I need to know how P over T changes with respect to V. Okay, and how I'm going to get that is from my ideal gas equation of state. Okay, so for ideal gas equation of state, I have PV is equal to RT. So P over T is just equal to R over V. Okay, so for the case of an ideal gas, have the ds ideal gas is equal to CV ideal gas over T dt plus R over V dV. So now I'm going to integrate this from my reference state to my state of interest. So I'll just put an I there for state of interest. This is just CV ideal gas over T dt, where CV is constant, right? Because CV is just Cp minus R, and Cp, we're given the value of it, and it's constant. So I'll integrate this from 0, right, as T naught to T. Okay, and then this I'll integrate from V naught to V, right, where R is just constant. Okay, and so what I end up with is S ideal gas minus S naught ideal gas is equal to, so Cp is or Cv and Cp, right, are constant, so I could pull that out, and I'd end up with Cv ideal gas times log T over T naught, okay, plus, R is constant, this could be R log V over V naught. Okay. All right, and so what I'm going to do next is simplify. Okay, so I've got V here, and V is fine, but in the problem we're defining our initial and our final state with P, so it'd be nice to have P instead of V. So I'm going to use the ideal gas equation of state again. Okay, and so key is going to be, so let me just write PV is equal to RT. All right, so if I had P naught, V naught is equal to RT naught. Take the ratio of the two. Okay, I end up with, so as an aside, P over P naught times V over V naught is equal to T over T naught. Okay, so V over V naught then is equal to T over T naught times P naught over P. Okay, so in terms of simplifying, so S ideal gas minus S naught ideal gas is equal to CV ideal gas log T over T naught plus R log T over T naught P naught over P. I play with my log rules. So this is CV ideal gas log T over T naught plus R log T over T naught. Okay, T over T naught plus, right? So this is would be the sum of logs. Okay, R log, okay, P naught over P. Okay, and then this is going to be CV ideal gas log T over T naught. Okay, oh, and actually, let me just, as I flip the sign, okay, I have a common log T over T naught. Okay, so this is CV ideal gas plus R times log T over T naught. Okay, and then I'm going to use a negative sign to flip this, so log P over P naught. Just so I keep it at P over P naught, just like T over T naught. Okay. Cool. Just doing a sanity check. All right. Yeah, because I've got the negative sign. Okay. So CV ideal gas plus R, well, that's just CP. So I end up with the final expression S ideal gas minus S naught ideal gas is equal to CP ideal gas log T over T naught minus R log P over P naught. Whew. Okay. So again, a little more cumbersome getting to the equation, but once we have it, we have it. Okay, so where was I for H? All right, so H, yeah, so ideal gas contribution is just Cp at delta T. Then I'd get the residual contribution. For entropy, it's just the equation for the ideal gas contributions. A little more involved, but I have everything. Okay, so let's go over and compute this. Okay, so going back over to my MATLAB code. Okay, so this is part B now. Okay, so for part B, I'm going to start by copying this code because I need my reference value. Okay, so let's get the residual part first. So we'll call that T naught and P naught. Okay, and then I'm going to calculate or copy this and update it. And I'll start by, so this could be H naught R, S naught R, and Z naught. Okay, I'm going to suppress those for now. And then I need to pass to this T naught and P naught. But boom. Okay, and then T naught and P naught. Okay, that was 266 Kelvin and 1 bar. 266 Kelvin and 1 bar. Okay, and we're told liquid, right? Yeah. Okay, so 266 Kelvin and 1 bar. Okay, and so I'm going to use T naught and P naught now and calculate H naught R and S naught. I'm going to run it because I should get 3 real roots. I want to confirm that I do. Then I'll update this to choose. Okay, yeah, so I get 3 real roots. Okay, so I'm going to make sure I choose the third one. So I'll select the liquid root and convert HR to joules per mole. So now this is going to be H naught R and S naught R. It's going to be H naught R3 and S naught R3. Okay, so I updated it, so I'm going to get rid of this. Okay, and so then calculating, I'll call it residual difference. Making note that H is in kilojoules per mole, is in joules per mole K. Okay, so dHR is equal to HR minus, now this H naught R that I just computed, and dSR is equal to SR minus this S naught R I just computed. Okay, and now let's get the ideal gas contribution, and we'll stick with H in kilojoules per mole and SR in joules per mole Kelvin. Okay, so dH ideal gas. Okay, well, first I need CP. CP ideal gas. Okay, it's the same as problem 2. Is it 96.5? 96.5. Okay, and that's joules per mole Kelvin. So dH, that's CP ideal gas times T minus, I call it TK minus T not in Kelvin. Okay, and then divide by 1,000, since this is joules per mole Kelvin, temperature's in Kelvin, so that'd be in joules per mole. So divide by 1,000, so it's also in kilojoules per mole. Then ds ideal gas is equal to Cp ideal gas times log T divided by T naught in Kelvin plus minus R log ratio of pressures. Minus R, okay, I need to define R, 8.314. Bam. And so R times log P bar divided by P naught bar. Okay, and I just need to make sure I'm using absolute pressures in the same units. Okay. As a note in problem 2, when we had to calculate the ideal gas contribution to the entropy change of our system, right, we just had this first term, right, but that was because in the last problem we had an isobaric process, right? So for an isobaric process, this is just 0, right? When P bars and P naught bar are the same, right, this would just be reduced to 0. Okay. All right, so that's ds ideal gas. So now computing H and S. So H would be equal to dHr plus dH ideal gas, and S would be equal to dSr plus ds ideal gas. Okay. All right, because our absolute value is how we're defining our 0. So our absolute value of H, right, it's just going to be the difference in our ideal gas and residual contributions. All right, so doing so then, I get the H. Okay. My absolute H is equal to 4.8192. That's kilojoules per mole. And S is equal to 16.6981. And that's joules per mole Kelvin. Whew. All right, so that's B. And now C. Okay. So enthalpy and entropy. So at 10 bars, 300 Kelvin. But now we're going to use as a reference state, hypothetical ideal gas state at 1 bar and 266 Kelvin. All right, so state 0 still is at 1 bar and 266 Kelvin. But now we're defining our 0 to be an ideal gas at those conditions as compared to the actual value. Okay, so all right, we got this. Okay, now as I work out my equations for my reference state, okay, I'm just going to go through the whole exercise again, right, to set up the relevant equations just to make sure it's clear where these things are, coming from. Okay, so so in general, I can compute H relative to H naught, right? I can calculate my enthalpy relative to some value at H naught. Thermo is all about differences. Delta U is Q plus W. Okay, so H minus H naught, right? Compute my relative enthalpy. Okay, in the spirit of chapter 5, I take my difference in enthalpy and I write it as an ideal gas plus a residual contribution. Okay, cool. All right, so now just like before, I want an absolute value of H, so I'm going to bring H naught over to the right-hand side. And I'm going to write this as H is equal to H ideal gas minus H not ideal gas plus HR minus H naught R, okay, plus H naught. Okay. Now in part B, we used an absolute value, or we took an absolute value at our reference state conditions to be 0. Right? So at T naught and P naught, we took the absolute enthalpy to be 0. Right? So we said H naught is equal to 0, and we moved from there. In this problem, right, it's going to be a little different, right? We're going to take the ideal gas value at T naught and P naught to be 0. Okay, so what I'm going to do is I'm going to come over to the next page just so I can keep writing this out. So this could be H minus H ideal gas minus H naught ideal gas plus HR minus H naught R, okay, plus, now H naught then I'm going to write as H naught ideal gas plus H naught R. Okay. Now, in terms of simplifying, I need to be a little careful. I just don't want to be too kill happy, right? I don't want to kill this H naught ideal gas with this H naught ideal gas and this H naught R with this H naught R. Because then I'd just be left with H is equal to H ideal gas plus HR, and then I can't compute anything, right? I can't compute an absolute ideal gas value. All right, I can compute an absolute residual value because actually those are relative values. Okay, but I can't calculate H ideal gas, right? I can calculate H ideal gas relative to something. So I need to keep this intact, right? And so remember, when I see this difference in ideal gas values, I say, okay, I can compute that analytically. Okay, when I see my residual properties, I think, okay, I can compute those using my using an equation of state. Okay, so I don't want to just go around killing everything, right? I want to keep this term intact because this is what I can calculate analytically. Okay. Then in terms of this term, well, this, I'm going to cancel this H naught R, right? We'll kill off this H naught R here. Okay. And then how I'm going to deal with H naught ideal gas? Well, this is where we're taking our reference state to be the corresponding ideal gas value at T naught and P naught. So at our reference state temperature and pressure, we're taking the corresponding ideal gas value to be 0. So we're saying H naught ideal gas is equal to 0. Now, I don't want to just cancel this with that or also set this equal to 0. This needs to stay in place because what I can calculate, what I can work out analytic equations for and calculate are differences in my ideal gas values. Okay. So I'm going to be left with H. Okay, and I'm just going to keep this as H ideal gas minus H naught ideal gas, okay, plus HR. Okay, so this is just HR. We computed that in part A. And then this is just my ideal gas difference, which we computed in B. Okay. And then I end up with the same thing for S. Okay. So this could be S ideal gas minus S naught ideal gas plus SR. Okay. Now this is going to be the same difference we computed in B. Then HR and SR is just what we computed in A. Okay. And so this is delta S, right? Is this equation? Delta H, that's just my CP delta T for this problem. Okay. Okay, but again, the note is, right, we go through this exercise. We don't want to cancel everything. So H naught R is going to cancel this to H naught R. We don't want to go canceling out H naught IG with H naught IG. Right? This, right, I need to keep this intact as a difference because it's this difference that I can compute analytically. Okay. HR, right, really HR's a relative value. It's actual relative to an ideal gas, right? And that's how I'm able to calculate absolute residual values. All right, so if I go back over to my code then, okay. So what I'm going to have for part C is, well, let me just call it HC for part C, is going to be DH ideal gas plus, now it's just what I call HR from A plus HR. All right, you're not delta HR, just HR. Okay, and SC, that's going to be DS ideal gas, which we computed in B, plus my residual entropy at my state of interest, which we computed in A. Okay, so there we go. So here we'll have that H is equal to negative 16.63, 0.7365. Seven three six five. That's going to be kilojoules per mole. And then S is negative 65.4877. And that was joules per mole Kelvin. Okay, cool, right? And DH ideal gas we had converted to, that was in kilojoules per mole. Then SR, yeah, everything was in kilojoules per mole, right? So there you have it. Okay, and now last but not least, part D. Okay, part D, enthalpy and entropy of vaporization at 1 bar. Okay, well that's 1 bar and 266 Kelvin. Okay. Sorry, so how am I going to get that? If I get my cursor back, here we go. Okay, the key is going to be, okay, so, I'm going to be at 266 Kelvin and 1 bar. So at 266 Kelvin and 1 bar, okay, I have vapor-liquid coexistence, so I'll get 3 real roots. The smallest z corresponds to my liquid, the largest z corresponds to my vapor, right? And I'm going to have a vapor and liquid at two-phase coexistence. So if I just, go through the exercise for H first, right, key is going to be delta H of vaporization is going to be equal to H vapor minus H liquid. Okay, so change in enthalpy and going from liquid to vapor. Okay, so final minus initial. Well, I could take that difference, I can write as a sum of an ideal gas and residual contribution, right? So for here, that'd be HV ideal gas minus HL ideal gas plus HV residual minus HL residual. Okay. All right, so now key is when I have these, this liquid phase and this vapor phase, right, they're going to be at the same temperature and pressure. So if I wanted to calculate this, right, so if I were to go back, delta H, right, of an ideal gas is going to be Cp delta T. Well, enthalpy of an ideal gas is only a function of temperature, so the pressure doesn't even matter. But I'm going to have some initial state and some final state, which are both at the same temperature and pressure. Okay, so the key is that this ideal gas contribution, right, this is just going to be 0. So I'm left with then delta H of vaporization is just equal to the residual enthalpy of my vapor minus the residual enthalpy of my liquid. So we calculated this, was it in B, right? And then in B though, we just selected the liquid root, which is the third root. Well, then the vapor is just that first root, which I didn't use before. Okay, cool. Okay, and then we end up with the same thing for delta S, right? So delta S of vaporization, right? It's S vapor minus S liquid. Okay, and so this would be SVIG minus SLIG plus SVR minus SLR. Okay. Now key is I have vapor-liquid coexistence, so I have this vapor and liquid, right? They're at the same temperature and pressure. So if I go back to my equation, my general equation for ds ideal gas, well, it's this big long equation, right? Did I box it in? Right? It's this big long equation. Right, but the two states are at the same temperature and pressure, right? So even though now enthalpy of an ideal gas is a function of temperature and pressure, the two states are at the same temperature and pressure, so that ideal gas contribution will be 0. So I'm left with just delta S of vaporization is equal to the residual entropy of my vapor minus the residual entropy of my liquid. So coming over to MATLAB, right, what I'm going to do is if I come back to where I was in B, okay, I just pulled off the liquid and vapor. Okay, I just pulled off the liquid phase, right? Because that's what I needed for B. Okay, but we did this in B. Right, this is at 266 Kelvin 1 bar. This is my saturation pressure at 266 Kelvin. Or that's my saturation temperature at 1 bar, which is what we're given in the problem. Okay. So what I'm going to do for part D then So I'm just going to paste this, right? And instead, what I'm going to have is I'm going to do dH vap. Okay. So what I need first is my vapor root. So this is my liquid root. So it's going to be it's vapor minus liquid. Okay, then I'll divide by 1,000, so it's in kilojoules per mole. Okay, so this is liquid, and so what I need is vapor minus liquid. So it's just be the first root minus the third root. Okay, before I just needed the third root, and I'll call this ds vapor. So if I run this, I've got dH vaporization, right? It's positive, right, which tells me I've got the order right. The enthalpy of my vapor is greater than that of my liquid. So I've got a delta H of vaporization, and that's in kilojoules per mole. Okay. And so let me, dH vaporization is 21. So this would be a 21.3533. Okay, kilojoules per mole. And delta S of vaporization would be 81.07, 81.70. That's joules per mole Kelvin. And that is all she wrote. So if you have any questions, let me know. But that's it for the problems for this chapter. Let me know if you have any questions, and I'll be here to help you.